Hey guys, welcome back. Day 19. We're going to continue some more empirical molecular formula problems. We're going to dive in with number 6 here. You got a compound was analyzed and found to be 53% carbon, 53.3% carbon, 11.19% hydrogen, and 35.51% oxygen by mass. The molecular formula, the molar mass, is 90. So you got what is the empirical formula and what is the molecular formula of the compound. All right, so let's dive in. We know if we have 100 grams, if we have 100%, right, 100 grams, so I'm going to write that out, 100% to 100 grams, right? That's a horrible G. Go there. Yeah. 100 grams. That means we would have 53.30 grams of carbon. We would have 11.19 grams of hydrogen and 35.51 grams of oxygen. All right? Because that adds up to 100%, 100 grams. We got our mass ratio. And remember, we got a mass ratio. We're going to go to a mole ratio. And to go to the mole ratio, we have to divide by the molar mass. Now, the molar mass of carbon, 12.01 grams per mole. Hydrogen, I have 4 numbers, so I will use 1.008 grams per mole, just to get that. 4 sig figs there, and oxygen, 16. All right, so if we do this math, again, I think we get 4.438 moles of carbon, 11.10 moles of hydrogen, and 2.219 moles of oxygen. So now I have a mole ratio. Divide them all by the smallest. In this case, the smallest looks like it's 2.219. So if I do 4.438 divided by 2.219, I get 2. For hydrogen, looks like I get 5. And for oxygen, of course, we get 1. So the empirical formula. C2H5O. Now, quickly, 12 times 2 is 24. Why would I do 12 times 2, right? Again, look at your periodic table, the molar masses, right? So I'll write it out. 2 times 12 plus 5 times 1 plus 16, right? That gives me about 45 grams per mole. The molecular was about 90 grams per mole. Right? And so 90 divided by 45 is 2. The molecular looks like it's C4H10O2. All right, so just like we did in the previous video, we had to figure out, we had the mass, we had the percents, made them masses, all right, and then we made them a mole ratio, and then we got the whole number mole ratio, found the empirical formula, found the mass of the empirical formula, all right, and so let me walk through that again. We had our percents, all right, so made them grams, divided by the molar mass to get the moles. Right, that's a mole ratio. Then we divided by the smallest to get the whole number ratios. So then we got our empirical formula, found the mass of the empirical formula, which was 45, figured out how many times 45 goes into 90, which was 2, and so we doubled our empirical formula to get the molecular formula. That's it. That is what we did. Hopefully that makes sense. Going on to the next one. Suppose a hydrocarbon compound, that means C and H is only it. It's burned and produces carbon dioxide and water, right? Burned is plus O2. Oxygen was here. So we have CH, and we don't know what C is, and we don't know what H is. And that is burned, and it produces CO2 and H2O. We actually have the hydrocarbon compound right here, but you don't necessarily know what that is. You might know what that is, but most likely we don't at this point in Chem 1. All we know that the number of moles of CO produced is 1 times the number of moles of water produced. So water and CO2. No. And I know that this is a 1.5 to 1. That's it. It doesn't matter what they are. Be 2 and 3. 4 and 6. I don't know what it is right now. I mean, I could know what it is. I know what the compound is. But you don't know what it is. Now, law of conservation of mass. C's. All the C's, right, are from the C's, right? And all the H's, and there's that 2 there, right? All the H's are there. So it looks like my empirical formula would be C1.5 H2. I can't have C1.H2. I need to double this, right? Because at 0.5 you need to double. You double both C3H4 as an empirical formula. Right? That's, again, law of conservation of mass. If I have 1.5 moles of carbon on the product side, right? So if we have 1.5 moles of carbon over here, it all had to come from here. And there's no other carbon sources. Here I have 2 moles, because of H2, 2 moles of H here on the product side. So it means I have 2 moles of H on the reactant side. And since we don't have halves, we have to double. Now that empirical formula, right? 12 times 3, 36 and 4 is about 40. Right? The molecular is about 120. So that looks like we are multiplying by what? 3. And so we got to multiply by 3 to get C9H12. And so you know the 9 carbons. Obviously, there's a carbon, there's a carbon, there's a carbon, right? Each intersection of the line is also a carbon. So those are the 6 carbons on the ring, right? And then you have the 3 C's, so you have 9 carbons. And then the hydrogens, obviously you have 3 here, 3 here, and 3 here. Once we learn how to draw these things, you'll learn there's a hydrogen out there, there's a hydrogen out there, and there's a hydrogen out there that is implied. It's just not written. Okay? You don't have to dive into those types of formulas until you get to like organic chemistry most of the time. All right? And so, but that's not how you do this one. Another law of conservation of mass one with empirical formulas. Uh-oh. Am I missing the one? Oh, there it is. Okay. Find the total number of atoms in a sample of cocaine hydrochloride, which I hope you do not take part in. All right, how do we do this? All right. Well, it's a long conversion. I have 23.5 milligrams. Milli is 10 to the minus 3, right? And I will put C17H22ClNO4 down. And now we'd have to do the molar mass. All right? So it is 12.01 times 17 plus 22 times 1.01 plus 35.45 plus the 1401 plus 4 times 16. If we do that, I got 339.81. of C17H22ClNO4 to 1 mole of C17H22ClNO4. Then we know that 1 mole of C17H22ClNO4 is 6.022 times 10 to the 24 molecules, 23rd molecules. All right. And then one more. We know 1 molecule of C17H22ClNO4 happens to have how many atoms? Well, 17 plus 22 would be 39, 40, 41, 45. 45 atoms. And so if we do all that math, I get, right, to 3 sig figs, 1.87 times 10 to the 21st atoms. That's a lot of atoms. All right. Last problem. All right. And just so you know, this is one of my Chem 151 top 5 favorite types of problems. And this is combustion analysis. All right. Now, in combustion analysis, in the time of this recording, and the current edition of the textbook we're using is not in this chapter. It's actually in a different chapter. That's okay. Right, those problems will show up when they show up. But this is a great time to do combustion analysis because it is a empirical molecular formula compound. We don't need a balanced chemical formula for it. All right. So you have in this, you have this much of an organic compound, right, containing C, H, and O. Was analyzed by combustion. It gives you CO2 produced. And it gives you water produced. It gives you the molar mass. And you need to determine empirical molecular formula of the compound. All right, so what does that mean? I have carbon, hydrogen, and oxygen. And we don't know how much of each. We just know we have a total of 0.1101 grams. And that's reacting with O2 to make CO2 and H2O. And we know we have 0.2503 grams of CO2 and 0.1025 grams of water. Okay. Here's the deal with this, right? In the couple problems previously, all the carbon, right? All the carbon is there. All the hydrogen is there. Everything has oxygen. And in fact, we have excess O2, right? Because it's burned in air. There's extra oxygen. We never run out of oxygen in air. If we ever did, we wouldn't need to learn any more chemistry because we wouldn't be here anymore. All right? And so, how do we do this? I have to first find out the amount of carbon here and then subtract from the original amount. I have to figure out the amount of hydrogen here and subtract from the original amount to get the amount of oxygen that was in the original compound. And then once I have the grams of carbon, the grams of hydrogen, and the grams of oxygen, I can do my empirical formula, if that makes sense to you. So let's do it. We'll show you what exactly I mean. So we're going to start off with 0.2503 grams of CO2. And we know carbon dioxide, well, 1 carbon and 2 oxygens, right? So 16, 16, and 12.01, right, give us 44.01 grams, 1 mole of CO2. Then we know that 1 mole of CO2 is 1 mole of C, right? And then we know that 1 mole of C is 12.01 grams of C. All right. So if I do that, it looks like I get 0.06830 grams of carbon. I have to do the same thing for water. 0.1025 grams of H2O. And we know water, 18.02 grams of water, 1 mole. And 1 mole of H2O gives me 2 moles of H, right? And then 1 mole of H is 1.008 grams. I have 4 sig figs, so we want to do that. And that looks like I get 0.01147. All right. So now we're going to come down here. 0.1101 grams of C, H, and O. And we're going to subtract our 0.0683 and our 0.01147 grams of H. And if we do that subtraction, it looks like I get 0.303 grams of O. So now I figure out how many grams of each of those atoms I have in my original sample. So now I can do 0.06830 grams of C, 0.01147 grams of H, and 0.0303 grams of O. And I have my mass ratio. What do? We go to our mole ratio. So carbon, 12.01 grams per mole. 1.008. Again, I'm using that because I have 4 sig figs, grams per mole. And 16 grams per mole. So it looks like we get 0.005687 moles of carbon. It looks like we get 0.01138 moles of hydrogen. And it looks like we get 0.00189 moles of oxygen. All right. Now, what do? We have to divide by the smallest. And it looks like oxygen's the smallest, isn't it? 0.00189. If we do this for carbon, looks like I get 3. For hydrogen, Looks like we get 6, and oxygen 1. So our empirical formula is C3H6O. And what does that weigh? Right? Well, 12 times 3 is 36, and 6, right, would be 42, and 16, 58. Right? So that's about 58 grams per mole. The molecular was 115, right, if you look at your sheet. So 115 divide 58 is about 2. So we got to double. So the molecular is C6H12O2. And that's it. All right, so let's recap this. All right, recap this. Combustion analysis. And one of the reasons we do this is you have a white substance. Most CHO compounds are a white substance. Did you make what you think you were supposed to make? Right? If you make aspirin, just a simple lab. A lot of times in Chem 2 we do it, or in Organic Chemistry 1 you'll do it. Right? You make aspirin. Right? The starting material, which is salicylic acid, it's a natural compound from a tree bark, right? Looks like a white powder. Your product, aspirin, looks like a white powder, right? Because when you make it, it doesn't come out like a pill. It comes out in like a white powder. Hard to tell if you made it or not, right? Combustion analysis is a technique, not what we do in lab. There's some easier tests, but it is a technique to see what you actually have, all right? And so what we did is we took our kind of an equation here, right? Reactants going to products. We know we had that many of grams of unknown CHO compound. I know how much product of carbon dioxide and how much product of water was made in mass. So I figured out the mass of carbon dioxide. I figured out how many grams of carbon were in that carbon dioxide. Then we figured out how many grams of hydrogen from the grams of water. Then we subtracted the grams of carbon dioxide and the grams of hydrogen from your unknown to leave you with grams of oxygen. And once you get to that point, right, all that above here is new. This below now is the old stuff, right? I have a gram ratio, gram, divided by the molar mass of each compound to get moles, moles, and moles. And once you have the moles, you divide by the smallest one, which was oxygen, to get the mole ratio. And that gives me my empirical formula. We figured out the mass of my empirical formula. The molar mass of the empirical formula was 58. And that double that to get 115, right? 2 of those go into the molecular formula. So we had to double the empirical formula to get the molecular formula. And that is how we did that one. So that ends day 19. All right, again, reach out if you have any questions. And that's that. We'll see you next time, guys. Take care.